Congratulations. I assume all of you have submitted your papers. Good work. That's got to be a load off of your shoulders.
I mean, yes, it is, but there's still more.
Of course there's more. I think that that's a great point, is that there is always more to be done. And that's not actually a bad thing. Because if there wasn't more to be done, I mean, A, we'd stop learning, but B, also, we wouldn't get that practice of dealing with being able to handle having more to do. Because there will always be more in life. Maybe that's a little bit of a tangent, but it is where we are. So, congrats on finishing those things. There's 2 different sets of slides going around. It seems a little bit light today in class. Maybe some students are finishing up their reports or something. Or yes, they're enjoying thanks. Well, anyhow, before we start today's lecture, I've got a couple of things I want to talk about. The first is reviewing the same thing we do every class, the most important concepts from last class. But I also wanted to clarify a couple of the concepts from last class because I know that we ended right at the end of most, which was fascinating and one of the most important concepts of class. But I think that there could be a chance for practice for that. So I want to give you guys another opportunity to see an example of using most. It's very helpful and gets used a lot. So it'll be a good chance for you to practice. And then there were 2 more concepts from last class I wanted to go over. Other than that, we don't have that many more classes. We really have 3, including this class. We have 1 more class after, today's the last class before Thanksgiving, obviously. We have 2 classes after Thanksgiving, and that's it, which is pretty fast. There's a lot more stuff for you guys to learn. There's always more that could be learned, but we're going to fit in the important things for the rest of the semester. Ian, did you have a question? No. Okay. So, the 2 concepts that I wanted to, well, let's start with the most important concepts from last class. Why don't you take a minute and write those down? Are some of the pages not stapled? Yeah. Ah. There was a problem with the photocopier. I'm sorry for... It's a good thing I brought a stapler as an example. Does anybody else need a stapler? Oh, would you mind passing it back?
Oh, I don't need one. Do you need one?
Oh, okay.
Sorry.
Then great. All right, most important concepts from last class. Still reflecting on them?
Most.
Yes?
Sorry, quick question. On the syllabus, there's no assigned reading for December 12th.
There's no class December 12th.
But the final's on the 19th.
Yes, because the last day of class is the 11th. Yeah. Good question. And the final exam is on the 19th between 5:15 and 7:30 p.m. in this room. Da, da, da. It's going to be the same style format as the midterm. It will be comprehensive, but it will be primarily focused on the content we've covered since the midterm. So what are the most important concepts from last class? Yeah, Janet?
The most calculations, which rely on use of they're not formulas, but sort of the patterns.
Yeah, the most operations, definitely. What else? Yeah. Kathy.
When you calculate normal time, you're calculating how long it would take an average worker to complete a task. And so you can extrapolate from there.
So normal time is an average worker doing what? Say it again.
Processing 1 unit.
Processing 1 unit. What else?
Using the standard method for working at a normal pace.
Exactly. So an average worker, average pace, standardized method, making one thing, one widget, one whatever it is, one tweet, one Facebook like, whatever. What else is a really important concept from last class? Yeah.
We did workstation component arrangement principles.
Yeah, the principles for workstation or component arrangement. Did any of you guys think about your kitchen related to that when you got home? Okay. And this point that Kathy pointed out about normal time, the other side of that equation is standard time. That's another really important concept because the standard time is what you end up having to account for when you're building something, when you're figuring out how many workers to have, all of those things. What else? So most is a certain type of work study. What else can we do to study work? Direct time study, absolutely. What is a direct time study?
Direct observation of a task using a stopwatch or other chronometric device to record the time taken to accomplish the task.
Amazing memory.
Yeah.
Yeah. So can somebody explain what a direct time study is, in other words? Yeah.
Like you would sit there with a stopwatch and an actual person physically timing them as they do the task.
Absolutely. Hopefully, as they do the task multiple times, multiple people. Yep. And you rate their performance. And there's two other methods that we didn't get a chance to cover. We're not going to cover them in detail, but I wanted to make sure I told you about them. And the first is standard data systems. Standard data systems are the fourth method, the third method, and the standard data systems involve using specialized pre-available data for your industry or more likely within your company to develop these standard times or normal times based on information you've already gathered. So like predetermined motion time systems, which are really useful for a large number of generic tasks, if your company is doing something that's really similar but in slightly different ways, say you're assembling a car, you're putting on windshield wipers in a bunch of different ways, but generically it's putting on windshield wipers, you can look back historically at how long that's taken for a bunch of different cars to make estimates. And that's what a standard data system is. Usually they're proprietary, but that's how a standard data system works. And then the last option is work sampling. And we didn't talk about work sampling, but work sampling, if you recall, and I'm going to, I guess, if you recognize that graph that we were talking about how long things take and how accurate they are, and then it was splitting out whether it's an estimate or what kind of time study or work measurement it is, the work sampling is in its own category because it's so different than the others. Work sampling doesn't really do a good job of figuring out how long a task takes. In fact, work sampling doesn't really tell you how long a task takes. What it tells you is what percentage of a worker's time is spent doing a certain task. And so the way work sampling works is you'll have a video camera and you'll record large amounts of data about what a worker's doing and then sample it at different intervals. And you'll record, for example, a great example is what Robbie's doing right now. He's recording me lecturing, and we could take all of the lectures that we've done for the whole semester and we could randomly sample them. And we could take, let's say, 100 samples. And we could figure out what percentage of the time am I waving my arm sideways versus pointing at the board versus just looking at you guys? And so from a work sampling standpoint, we can figure out what percentage of the time am I doing some hand gesture versus pointing to the slides or writing on the smartboard. And so work sampling allows you to get an idea of the breakdown of percentages of time. Not how long should you allocate for one task or another, but how is the current time being spent. And that's why work sampling is so different. So how might you use work sampling compared to direct time studies? When might you want to use them? Yeah, Elena.
How many samples do you have to take?
That's a good question. So the question was, how many samples do you have to take? And it depends. No, it does depend on the variety of work and on how many workers and things. So if you're looking at somebody who's, the easy answer is it really depends a lot. Because if, let's say we're looking at work sampling for a professor, and you only install a video camera in my office, well, you're gonna have to take a lot of samples to figure it out, because often I'm here, or I'm working from home, or I'm meeting with another research colleague. And so the sampling is gonna depend on that. So in the past, there have been some really cool studies done of, say, workers who work in a field picking food. And so if you want to look at how they use the truck, for example, and how they're loading the truck, well, that's a very small percentage of their time. But if you look at their whole day, to understand the area around the truck, you end up taking a huge number of samples. I know it's not a great answer, but you basically need a statistically valid sample size, and that changes a lot on what you're measuring. Okay. It is worth pointing out that the lecture slides for last lecture are really long. Did you guys notice how many slides there are? There's like a lot of slides, 174 or 173. And that's because there's a great depth to time studies, most analysis. The father of most analysis, or mother of most analysis, which is MTM, measure times management. There's stuff on work sampling, on standard data systems, and there's a lot more detail that you might need to know later in your career. So I wanted to make sure that was available to you, because I do think that each of those sets have a lot of really good, useful information for them. So that's what all of those additional resources slides are for. Other questions? So, in office hours today, I was answering a couple of questions about MOST, and I thought that they might be useful for most of you to go over as a refresher of MOST. So I wanted to talk about how MOST works, because we have these general moves, controlled moves, and tool use. And so grab your MOST handout, and I wanted to go over an example with you. We'll go over an example of reloading the stapler. So I'm going to put it in front of Samaya, and I'm going to reload the stapler. So I'm here at my desk, and let's say I realize, oh no, today I forgot to load my stapler. Okay, let's go do it. Well, I'm already standing, so I'm going to walk over to my stapler. So 1, 2, 3 steps to walk over to my stapler. So first, we're getting the stapler. And let's say I want to reload it on my desk here. So we're going to do a general move to get my stapler and bring it to my desk. So actually, why don't we say that my desk is right here, if you guys don't mind. Sorry. So, okay. So I walk over, it takes me 3 steps to get to my stapler. I pick it up. I'm not bending or rising, so I'm just picking it up. It's within reach. And then the next thing I'm going to do is I'm going to put it over on my desk. So 1, 2, 3, 4, 5, and then I'm going to sit. And so by doing that, when we look at the body motion aspect, I go from sit, or bend, or rise. Stand or sit, basically. What does it say? It says sit or stand. And so that changes the index now of this general move. So I've completed one general move. What's my return distance? Nothing. I'm not returning anywhere. So now I need to open my stapler. Well, opening a stapler is an example of a controlled move. It's a controlled move because I can't move it freely around in space. I have to open it in this particular way. So it, just like opening a cabinet door or the door to the office or anything else, it's constrained in the way that it rotates. That makes it a controlled move. So I've set it down on my desk. That was the put, right? I finished my general move. Now I have a controlled move. Well, the start of a controlled move is this get. Well, I don't have to get anything. It's already right here at my desk. So I have, for my A, B, and G, all zeros. And then I get to my controlled move, the M portion of my controlled move, and I'm going to open the stapler. So that motion is probably a foot of total travel. Okay, in the example, I'm not actually lifting it up. I'm just moving it in a controlled manner across the table. So because it's hinged, it's a controlled move. And because it's a controlled move, we're going to have an index of 1. So it's going to be less than a foot, or about a foot. And then we don't have any process time or alignment. I'm just opening it. So once I've done that, I don't have any return. That's it. I'm now ready to open my stapler. Yes?
Can you give an example of something that would have a process time?
Yeah, sure. If I want to send a text right now saying, I'm in ISE 210, right? I have to get my phone, I have to unlock it, which is going to be some of these keystroke aspects that you have under equipment use. And then, because I have an old phone, I'm going to have to type and then hit send, and it's going to take like 10 seconds. And that processing time, I'm just sitting there going, come on, phone. And that would be an example of processing time. The same would be true if you're making a peanut butter and jelly sandwich, the time that it takes for it to be in the toaster. Yeah?
So how can we differentiate a controlled move from a general move?
Yeah, a controlled move, the difference between a controlled move and a general move is whenever the movement is constrained. So if you're pulling a drawer out, if you're opening a door, any time that you can't just move in free space, you have a controlled move.
So the stapler, because you can't open it all the way, or like it's
Because I'm not just going like this. I'm not just waving it around to open it. I have to actually move it. I'm ignoring the step of unlocking it, but I have to move it in this manner. I can't just like lift it up to my hand somehow. I have to open it onto my table, following that path. Yeah.
So like smearing peanut butter on your sandwich is also controlled? Because it
Ah.
has to be in a specific.
That's a great question. So is smearing peanut butter on your sandwich a controlled move? Well, that's a great question, one I've thought about a lot. Because I don't think it is a controlled move, because it's not like I'm picking up peanut butter with my hand and then taking it and sliding it across the surface. I'm actually taking a knife and spreading it. And so if it's spreading it, I think that it's a tool use that's probably similar to something like a surface treatment, where you're wiping or using some other kind of, yeah, I think wiping is probably the closest of all of the different options under tool use. And so if we were making a peanut butter jelly sandwich, for example, we might use wiping at an index of 3 for soft with a certain square footage. I'm sorry, an index of 3, which would be half a meter, which is the smallest index for wiping, for example. And so the important thing to know about, and you bring up a good question, always peanut butter and jelly sandwiches are good questions. But when you look at the tool use setup, it goes get, put, and then tool action where you see an asterisk or a star. And that asterisk is where you substitute in whatever letter the tool use would be. So in this case, it would be S, surface treatment. And then you'd put in the index for surface treatment. And then you'd assign the tool, and you might return to another starting position. I actually know how to reload this. Oh, there we go. Okay, so let's continue loading a stapler. So I've done my controlled move to open my stapler, following that arc. And now my stapler is open. Right? Well, I have to now get my staples. Let's just assume that I have my staples just sitting on my table. They're not in a box, right? Let's just save some time here. I'm just going to grab those staples. So that's how I get the staples. I don't have to arise. I don't have to go anywhere. It's a general move to get my staples. And then we have to come up with the tool use for how you load a stapler. And we'd have to pick the tool use that's most similar to loading a stapler under the tool use of loading the stapler. Just one sec. So for loading a stapler, you might have, it's a tough one. You'd probably have something similar to securing a cotter pin.
What is a cotter pin?
A cotter pin is the pin that goes through a bolt so that it can't be pulled out. But you'd have to make an assumption about what you think is the best tool use to mimic putting those set of staples in. Sky, I saw a question.
Oh, I was going to ask where you found it on the sheet that I found.
Okay. Yes, Elnaz.
So if you go with securing cotter pin, that would be C cut, and then you would put that under tool action in the table.
Securing a cotter pin would be undercut, and so that would go in place of the star.
This star. Okay.
Yeah, and actually you wouldn't need the general move to get the staples. That would be part of the get tool, right? So you'd get the staples, and then you'd secure that. You'd do the action. Yeah, Elena.
So are you using secure cotter pin as like a reference? Like, is it harder than that?
I'm thinking about secure cotter pin as something that's similar to loading staples. That's either similar to and slightly harder or the same difficulty.
So if you felt that it was slightly harder,
Then you'd have to go to a
index of 24.
yeah, you'd have to go up to a higher index. Yeah. So now I've loaded my staples. Yes.
So were you saying that getting the staples and loading them into the stapler was part of the same move?
Yeah, that would be part of the same tool use move, because I don't need a general move to get the staples if I can use the get tool of staples. Gareth.
Kind of process.
Okay.
You're saying.
Now I have a controlled move of closing my stapler. And when we look at the controlled move list, well, my controlled move, first I don't have to get anything. I do my controlled move, and now I return. Well, again, I don't have to return anywhere. Yes?
Wait, was closing the stapler part of aside to you?
No, the closing the stapler would be the controlled move. You don't aside the staples because they're already inside. When we do the tool use of loading the stapler, we're saying that the tool is the staples. So you wouldn't need to then aside the tool because it's already,
What does aside do?
aside the tool means set it aside. Yeah.
So what do you do if, like, sometimes when you load a staple, you have extra staples and you would have to put staples?
So then you'd aside the tool, yeah.
But if you're doing like a general calculation, how do you do like account for variability like that?
Yeah, that's a good question. So if you're going to do something like, well, maybe the staples are too long, so you're going to have to break some off and then put them back in the bowl of staples, for example. What you'd do is you'd make several different most charts and then weight them by the frequency that you expect that task to happen to figure out an average time. And then you use y equals mx, no, I'm kidding. So I've put my loaded it with staples, that's my tool use, and now I have a controlled move of closing it. So I've closed my stapler. Okay, close my stapler. There's no return there, but I do want to return. I want to go back over there, guys. But I can't return with my tool use, my controlled move, because all I have in a controlled move is the A for return. It's that action distance. I don't have the getting something and the putting something of a general move. So now finally, I've loaded my stapler, just putting my cell phone away, loading my stapler, and now it's time for me to return, which will be a general move because I'm going to get my stapler, I'm going to arise or stand up, and I'm going to walk back to where Samaya is to put the stapler back down where I found it. And then I'm going to return to teaching you guys. And so that would be one general move. I'm getting it, I'm putting it, and then I'm returning to somewhere else. When you add up all of those different moves with a bunch of zeros, right? Because some of them had like 0 action distance, etc. You find the total index, multiply it by 10, and then use the conversion to convert to seconds. Yeah, you can. Yeah, you add them all together. The order doesn't matter. You can convert each one to seconds. You can add them all together and convert to seconds. I don't care. Yeah, Ian.
So just the return is then just the action distance. That's it.
The return on the controlled move.
No, the general move.
The return on on the general move. It's just the action distance. So it's after I've put this down, do I go somewhere else? So I could like put this down and I could just leave. That would be my action distance. Technically, they call it a return, but it could be go to wherever. So I could return to teaching. I'm just calling it return, but it could be I could go over and do some other task over at your desk.
Okay, so when you took the stapler and then moved back over there, that technically wasn't a return. That was a complete new process.
This is, yes, you're nailing the difference here. The nuance is that in the language of most, that was a general move. In the discussion of what is it Dan's doing right now, he's returning the stapler. Because we call it in English returning, right? But we could say it as placing the stapler back where he found it, to not use the word return, which we also use in most. So I was returning a stapler. I wasn't doing the return action of most. Yeah, Yifei.
What if you trying to return the stapler and using it on your way back?
Whoo-hoo, that would be exciting. What would happen if I'm using the stapler as I'm walking? That's a good question. Okay, so I've closed up my stapler. I'm sitting here. I feel victorious in my battle against a lack of staples in my stapler. And I want to use it on my way back. So, do you mind if I borrow these for a second? I have these 3 sheets of paper on my desk here. And I want to lift it up, put it in my hand, staple it, and then put them down. And then return to teaching. What would we do? It's a great question, Yifei. So, take a second and write down what you think we should do.
So the locking is a general move, and then the stapling is a control move, and then you do the separate calculations for that.
One of their equipment is
Yeah, we can use that one.
but there's gets wood.
Yeah. And then these
I would only add this.
So what would the answer be, guys?
Radio turning.
What can we do? I'm here, and I want to staple while I walk. Yeah, Alnaz.
What would be the longest time, which is the time that it takes for you to get to the desk?
Am I going to be able to go the same speed that I would if I'm stapling? Probably not. Yeah.
Would it be, so whenever you have the general move until you get to the point where you staple, and then that would be classified as equipment use?
Yeah.
And then after you finish using stapling, then it's another general move when you continue walking from that point?
So Ian found that there is staple, which is an index of 3 of equipment use. And so because, Ian, if you notice that you have, in equipment use, you have get, put, use equipment, aside, and return, we can use that to cover all of the bases of the general move too. So I'm going to get my paper and my stapler. That's going to be non-simultaneous hand movement. So it's going to be harder than if I'm just using 2 hands on one thing. And then I have this action distance to get, oh, sorry, that's not to get. I have my put, that's going to be really not necessary because that's just me moving. I'm going to use the equipment, which is going to have an index of 3 for stapling, and then I'm going to aside my items, which is going to be put them back down, right, at Samaya's desk, and then return over to lecturing. So it'd be 1 equipment use would be the answer for that. Uh-oh, I see some confusion. Yes?
So, I see the staple column on equipment use,
Yep.
and you got a 3. I was wondering what,
Why a 3?
yeah.
Because I'm either using a hole punch, a hand stapler, or I'm removing a stapler. I'm removing a staple, opposed to using an electric stapler. So basically, what this task would be is that actually, as I'm standing up to walk back over here, I'm just doing that task at the same time. So that equipment use is including my travel back. You could imagine that instead of doing that, I'm getting my paperwork, I'm standing up and getting my papers, and then I'm walking over here, which is going to be the action distance of the put part of the equipment use. Then I'm going to use my stapler, which is going to have that star of use equipment, and then I'm going to aside the things I've been working with, my stapler and my paper, and then return to wherever my next task begins. So if you add up all of those different types of moves, so for each type of move, you sum the indices, multiply it by 10, and then multiply it by the conversion to seconds, you'll have the total time in seconds. And like Justine said, if you want to think about some unlikely events or multiple possible outcomes, you can weight those different times by their probabilities. So if sometimes I do that staple thing on my way back and sometimes I don't, let's say half the time I do and half the time I just walk back, we can calculate the times for both those and find the average of the two. And that'll be the average time. Is that the average normal time or standard time?
Normal.
Exactly. It's the average normal time. Yeah, Elena.
What's the difference between tool use and equipment use?
Good question. The difference between equipment use and tool use is really just your options there. So think about it as more tools is fine. One of the key concepts that people often mess up with most is that you can't just build your own alphabet. You can't just say, well, I'm going to action distance, and then I'm going to stand, and then I'm going to get, and then I'm going to controlled move, and then tool use, and then idle time, and then, I don't know, you can't just put it all together. You have to have a general move, or a controlled move, or a tool use, or equipment use, even if they have a lot of zeros in them, over and over and over. Yeah, try it.
So this is sort of going, like repeating probably what you said before. So return doesn't matter wherever you're going. It's not returning to the origin. It's going to wherever. So that's why you don't have to build in the general move when you finish doing something and go somewhere else.
Yeah, the return doesn't necessarily mean returning to start. It just means going somewhere. Often, if you're doing repetitive tasks, you're returning to start, but it doesn't matter. Yeah.
If you are standing up, then it goes to the general move. If you need to return, through returning you need to stand up?
Yes, that's a good point. If returning involves standing or sitting, because all you have is this return of action distance, you don't have sitting or standing, you don't have anything else, then you do have to add a general move. That's a great answer. So if returning means going and sitting back down, that's a general move. Absolutely, just like you said. It'd be a very boring general move because it's action distance and then body movement, and that's it. But it's a general move.
Okay. So in doing that, then you wouldn't you wouldn't add it in twice. So put in
No.
a value for the previous return and then, yeah, so you don't, which one would you choose?
Well, so if the return would be to go and sit down, I would have 0 for return, and then I would have a general move of going and sitting down. All right. Let's move on, generally move on in a controlled anyhow. We're going to move on, and we're going to talk about manual material handling. And so the rest of today's lecture, well, I guess I didn't quite tell you what we're going to cover in the rest of today's lecture. We're going to cover manual material handling. We're going to cover injuries and cumulative trauma disorders specifically. And we're going to have a guest lecture if everything goes to plan.
About what?
That's a good question. We will see later. It's a vision-related thing. Yeah.
Who is it?
It's a person. His name is Jeff. It's actually a former student of 210 who uses the vision stuff in his work. And he should be coming later this evening, close to the end of class. If you attended HFES, you may have met Jeff. He was there. Anyhow, if not, then you didn't. So ha. All right. Biomechanics and manual material handling. As I get ready for this, I want to turn on my lights because this is a bright topic. That was not really a very good joke, but it is a topic that warrants extra attention. Does it make it harder for you guys to see?
Didn't do anything.
Didn't do anything for you, but it worked for my workplace. All right. So we're going to talk about biomechanics and manual material handling. Here's an outline of what we're going to cover. We're going to cover what the heck are we talking about? Static models. And so if you haven't taken physics recently, which I assume most of you haven't, we're going to do a quick refresher. Don't worry, I'm going to be here to walk you through it. We're going to talk about low back biomechanics, lifting limits to assess the maximum amount people can lift, and then some countermeasures. So, manual material handling is the set of limits that we apply to doing things to other things. When you talk about lifting, pulling, pushing, carrying items, manual material handling limits and calculations are there so that we can figure out how much can we safely do. So just like predetermined motion time systems allows us to figure out how fast we can do things, manual material handling allows us to figure out how much can we do. And these two things go hand in hand. And not just because we're talking about using your hands on these things, but they really integrate very closely in figuring out how fast can you do something and how much it weighs, how big is it, how awkwardly is it set up. So, in almost any industrial setting, there's manual material handling. And in a lot of other places. In healthcare, material handling also includes patients. In your work, material handling probably includes your laptops and your notebooks, the big old textbooks you might still have. That's manual material handling. Manual material handling is expensive. Oh. There we go. Manual material handling costs billions of dollars annually in workman's comp. Poorly designed manual material handling is responsible for all kinds of problems in industry. And if you think that these problems don't extend to the areas of work that you might work in, then I would caution you to think again. The way that Amazon designs Amazon Fresh, where they have people, or Google Express, where they have people going into stores and shopping for things, putting them into a bag and then carrying them to people's houses, deals with manual material handling. That 2-hour guarantee, how many things do they have to handle in those 2 hours? What's the weight of that bag of cat food that they're getting at Costco? And can they safely do their task throughout the day? The same is going to be true for any other material handling. If you're loading baggage as part of the Uber app when you get picked up at the airport, you, as somebody that works for Uber designing the app, need to take into account the manual material handling of the worker who's driving the car.
They never do that. You have to carry your suitcase yourself.
That's also, now we're talking about another aspect, right? So if you go and work for Uber or Lyft, how do their design decisions in the app impact the safety of the workers and the customers? This stuff matters. So the occupational biomechanics is dealing with the mechanical assumptions and calculations of the way the body works in workplace scenarios. And where do I think work happens? Everywhere. Exactly. Work does happen everywhere. So, muscle strength is one of the aspects that we use in this. Static strength is often thought of as how much we can, say, grip something that doesn't move or hold something still without our arms falling down. And dynamic strength would be, say, the amount of weight that you can lift, things that are moving. Some examples of forearm flexion and extension. And you might be thinking, the average male worker can basically curl 62 pounds, but that's not true. Because, just like we was briefly mentioned on the previous slide, dynamic work includes the rest of the body too. So using your back muscles, using your shoulder muscles, it's not just the preacher curl or some other isolated movement. So what we're going to talk about is using simplified biomechanics models, simplified free body diagrams, basically, of the forces that are associated with the body to make the calculations of the forces on somebody's body. So let me give you an example. And the good example is a static model. A static model assumes that nothing's moving and tries to figure out what forces are going on inside of the muscles or inside of the bones or things like that. So we take a 2D approach to simulating, say, how the arm works in this case. And because it's static, it's in the name, we're making the assumption that there's no movement. We're trying to figure out the static load, is what it's often called. And so what we're saying is, if I take my forearm and I make the assumption that it rotates around my elbow, that the center of my forearm's mass is roughly halfway along the length of my arm, and that I can figure out the weight of my arm, and I can model how much weight I have if I have something in my hand. So if we want to figure out what's the force at my elbow and the moment at my elbow, that's the rotational force. So the rotational force pushing my elbow to rotate down, if I have something that weighs 20 kilograms, so it's about 44 pounds, in a static position with both arms. So if I'm holding something like this, and we want to figure out how much weight is pushing down to my shoulders, and how much rotational force is my elbow experiencing, or do my muscles have to counteract, that's what we can do using a static model. So we're going to make some assumptions here. The first assumption is that my forearm, is 36 centimeters long. And that the weight of each forearm and hand is 16 newtons, with the center of gravity being halfway from my elbow to the tips of my fingers. Remember, the question here is going to be, how much is the force on my elbow downward? So what's the force downward here? Meaning I have to have an equal force upwards in my shoulder to hold that up. And what's the rotational force trying to cause my arm to rotate? From having a 10 kilogram weight in each hand. That's the same as saying a 20 kilogram weight split between my two hands. So we have 10 kilograms in each hand, and the load at each hand is the weight multiplied by gravity. So we have a total force of 98 newtons downward here at my hand. And this distance is the length of my forearm, which is 36 centimeters. The elbow force, the reactive force from my elbow to lift up my arms, needs to be equal to the sum of all of the forces. And the sum of the forces is the weight of my forearm, which is 16 newtons, here at 18 centimeters out, 16 newtons plus 98 newtons. So the force required on my shoulder to keep my arm from going down is 114 newtons. Questions about this? Yeah.
Where does the distance and the length of the forearm come
Great question, Ian. Ian said, where does the distance, the length of the forearm come into play? I think that's verbatim what you said. And the answer is nowhere. When we look at purely reactive forces and we're assuming nothing's rotating, it doesn't come in yet. It will come in when we want to figure out the rotational force. That's where it's going to come in. But in just figuring out what's the downward force, we're assuming that it's not rotating yet. Yeah, Ashta.
So does the direction matters here? So right now you're lifting this. If I'm pulling it, will it be plus 20?
Ah, good question. So if you're pulling down on something,
Yeah.
well, now the weight of my arm actually helps me
Okay.
instead of hurting me. Right? So if I'm pulling down on something, the weight of my arm helps me pull down because my arm weighs, in this case, 16 newtons. Yeah. And so to Ian's question, what's the reactive moment required to offset these weights? So why is my arm not doing the robot? We know it's not falling down, but why am I not doing the robot? The sum of all of the moments, and a moment is the rotational force around a joint. So it's the force that rotates around some axis, needs to be equal to 0. And the way that we use this is we have the force multiplied by the distance away from the point of rotation. So 18 centimeters is the same as 0.18 meters. 0.36 meters is the same as 36 centimeters. And we have the forces. So the way to calculate the rotational force is the distance multiplied by the force all to some individual point. It's how we figure out what the moment is at a particular point. And so what this is saying is that the rotational force on my elbow is 38.16 newton meters. Elnas.
Can you define what moment is again?
Yeah, moment is the rotational force about some point. So if we think about these doors that automatically close, they're hinged. The moment is going to be in the center of that pin of the hinge. And as I'm pushing the door open, I'm causing it to rotate, and the spring is pushing back on me. And so when I'm pushing on the door, and the spring is pushing back, and I'm pushing out at the outside of the door, I have to put less force on it than if I'm right at the very inside of the door, because the distance is further away from that point of rotation.
And if that moment didn't exist when you push the door, it would just go straight up.
The whole door would just fly forward in some cool, crazy physics way. If the door wasn't attached, is basically what we're talking about. Yeah. And so what's neat about this is that we can then make some cool calculations. So we're talking about a 10 kilogram mass here. That's about 22 pounds. And let's make a cool calculation. I think it's cool, anyhow. So we've got our point of rotation. We've got our 10 kilogram mass. We've got, and this is, remember, 98 newtons. We said this was 16 newtons. And this is 18 centimeters. 36 centimeters. So, we calculated the moment. Let's see if I can guess what slide we were at. We calculated the moment as 38.16 Newton meters. So the rotational force this way is 38.16 Newton meters, which means that because my arm is not rotating, there's an equal and opposite force rotating the other direction. But there isn't. There's not some magical like crank inside my elbow. My elbow's just staying still. There's some other force on my arm. What's that force?
Is it coming from your bicep?
Exactly, it is coming from my bicep. And so if we make this really simplified model of my arm, or of your arm, we've got this weight, right? And we have the weight is going down, the force of your arm wants to go down, and you've got this tiny little muscle that connects right there, really close to your elbow, and it's pulling so hard to make sure that your arm doesn't rotate. So let's make an assumption. Let's make the assumption that the muscle attached to your forearm, that this distance right here, this tiny little distance, is actually 2 centimeters, or 0.02 meters. Well, to offset the moment created by all of this other rotation, the force here and this distance is 2 centimeters. The force here is equal to what? Well, the moment arm at the elbow is equal to 0, is also equal, that's why it's not rotating, is equal to 38.16 Newton meters times x, and x gets multiplied by, I'm sorry, it's not times, it's minus, gets multiplied by 0.02 meters. Super small number. So, if we calculate x, what do we get? Let's do the quick math.
So you're finding the force that the muscle is.
Mm-hmm. What? So, 1608? I don't think so.
See, 1908.
So we have 38.16 equals x times 0.02. So divide both sides by 0.02. And you have x is equal to 1,908 newtons. Seems like a fair amount, but nobody knows what newtons are. That's just magical weird stuff, right? We live in America, so we don't deal with newtons. So we have this number of newtons, but to convert from newtons to kilograms, 1 kilogram, oh gosh. Uh-oh. 1 kilogram. Well then, that's not working well. Okay, so to convert our x from newtons to kilograms, what we want to do is we want to divide it by 9.8. That's going to convert it to kilograms for us. So you're dividing it by almost 10. And so we have 194.7 kilograms, which is the same as saying that x is equal to 428 pounds. So the next time you go to the gym and somebody says, oh, you can only curl 22 pounds, you can go, that's not true. My muscle can pull 428 pounds. What can yours do? Because that's the force in the bicep. Because it's acting over such a small distance. Just kind of crazy to think about, right? Yeah, Elena.
I don't understand why you're subtracting x times 0.02.
Because we have to offset, we have the rotational force in one direction, the rotational force in the other direction has to be equal to, has to make the total moment equal to 0. So it doesn't rotate. So the moment equals 0.
A positive moment is going counterclockwise, right?
Okay, so if we're talking about the actual sign, then you have a negative moment for 38.16 and a positive moment for the other one. Conceptually, it doesn't matter. They're equal and opposite. Make sense? I saw another hand back here. Okay. So that's kind of neat, right? It's crazy to think about how strong our muscles are. And using these relatively simple biomechanics and making some really simplified assumptions, very simplified assumptions, we can get rough forces in the arm. Yes?
So, if you use somebody with longer arms, would have to use more strength to force in their muscle to counteract the same weight, right?
This guy's got a great question. Somebody with a longer arm would have to use more force. That may or may not be true, Sky, because what matters is how this scales. If that 2 centimeters is the exact same 2 centimeters, then definitely. But if it also gets bigger, then no. So that's why when people talk about Olympians who just have this geometry or the biomechanics to do really well in the Olympics, it's because, say, their attachment point is just a little bit further out than everybody else's. Or their limbs are just a little bit longer. And all of those things work to their favor. So now that you know a great pub joke for when you're talking about lifting weights and you want to do some quick math, we're going to move on. Yes, Jarnett.
So going back to the previous one, I know you want to move on, but why are you taking the distance, the 2 centimeters, as opposed to the length and the length this way?
You're taking the 2 centimeters because you're only focused on where it attaches. We're assuming that it just pulls up where it attaches.
Okay.
Just like if I'm holding a stick or a spear or just a 20-pound weight, it doesn't really matter.
Okay. So like
The weight in my hand is the same amount.
Okay, so that line that's 2 centimeters away, that is the muscle.
Yeah. Yep. So let's talk about low back biomechanics. Perfect timing to do stretches. Great idea. All right, hands together. Shoulders up and back, and then head all the way up. And head all the way down. Good. Hands together, arms out in front of you. And reverse. Good. 1 foot forward, turn your shoulders, and then your head. Be careful, don't hurt yourself. You can't win at stretches. And trade, shoulders, and then your head. Excellent. Have a seat. Thank you for reminding me. It's a good segue. It's a good segue to talk about low back biomechanics. So, low back biomechanics is doing these same calculations, but instead of just having the force of the arm and having everything be horizontal, things are more complicated. So if we look at somebody lifting, the muscles in their back act over this very short distance, 5 centimeters, where the muscles attach outside of the point of rotation. And so somebody has their whole upper body pulling down on them, their head, their arms, and a weight, all pulling down, trying to create this rotation around your trunk. So if we have an example here where 40 centimeters out, we have a load of 200 newtons. If you're trying to think about how many kilometers that is, how many kilograms that is, you can divide it roughly by 10. So it's about 20 kilograms, which is about 44 pounds, just to conceptually understand how much is a newton. We also have the weight of our torso and the distance of our torso. Then the muscle force, the force in that muscle, is 3,200 newtons. It's a lot.
Which muscle is that?
This is the lower back muscle that's pulling your back up, resisting the rotation. And so that's a lot of force inside that small muscle. There's also a compressive force compressing your back. Right? If you think about me standing here, everything, say, above my hand right now is pushing down on my back that's below my hand. I mean, it's not exactly rocket science. All of my weight is pushing on my shoes. It's the same for your back. It's just everything above that part of your back. But when we're at an angle, like this dude is, when we're at an angle, then you get a compressive force in the back along the line of the back. And by calculating, picking an angle and making these same calculations, we can calculate what's the compressive force on the discs in the back. The important thing to note is that the muscles in your back and the structure, the architecture of your back, are subject to tremendous amounts of force. Yeah, Gareth?
Was the angle from parallel to ground hips?
Yes. Yeah. Good question. Just like when we were dealing with light, it's going to be the angle from vertical. That's a great question. So, we've learned today a few things. I think a lot about making peanut butter jelly sandwiches. We learned the most important concepts from last class. It was most. And how to do static modeling of the back and of the arms for forces. And we could do the same thing for our legs if we make some assumptions about the lengths of our legs. I don't think people are doing a lot of lifting with their legs, but hey, if you're going to put something on somebody's legs, sure, why not? Same thing. So how do we use what we've learned and all of the research that's been done to figure out how much can people safely lift? This is important because when we think about asking people to do tasks, we want to set up allowances, we want to set up normal times and standard times for them to be successful. We also want to set up weights for them to be successful. What's neat about combining predetermined motion time systems and what we're learning today is that you can do important calculations. So let's say, for example, that the US government decided they actually did want to support Puerto Rico and send troops to help sandbag the island to prepare for the hurricane that was coming. And they thought, you know what, let's just magically assume that we're going to build a wall around the entire island of Puerto Rico that's going to be 4 feet tall, 3 feet tall. We're making some really broad assumptions here. If we were going to make this assumption, well, we need to know how many workers and how much sand and how long we have to do this. So we can do a predetermined motion time system to figure out how long it takes to fill a sandbag, right? Each scoop of sand, putting it into a bag. And we can also do predetermined motion time systems to think about how long it takes to place the sandbag. But we need to know how heavy the sandbags can be safely for the workers to be able to do this, and what's a standard time that we can allow for filling sandbags so that we can calculate how much sand, how many bags, and how many people do we send to the island to build this wall before the hurricane comes that's going to be of a certain height, certain width, and a certain length. And combining what we're learning here and what we learned last class, okay, that's a bit of an extreme example. We're not going to make a wall all around Puerto Rico to keep the hurricane out. But when we talk about the gigafactory and manufacturing, certainly loading batteries into a Tesla car or unloading an airplane, these same concepts apply. We know the total square cubic footage inside of the hull of an airplane. I mean, we don't. I don't happen to know it, but the airplane manufacturers and the airlines certainly do. And they know roughly the density of luggage per cubic foot. So they can think about how long and how many workers do they actually need to be able to turn a plane around at the gate in a reasonable and safe amount of time. And if they add more workers, how much time will they save? And when you combine that with all of the other costs related to keeping an airplane on the ground, you're not making any money, you have to pay the crew for that time, all of the other things, you can very carefully balance that equation for how many workers should you have working at the airport. And how long is it going to take for you to get your luggage at the baggage carousel? That's what you're going to learn today, if you combine it with the last class. And that's kind of neat. So, not surprisingly, 1472G has a standard on lifting. It's called the one-size-fits-all approach for setting a lifting limit. This is for lifting tasks. So the Military Standard Handbook, and it's on page 205, has information on single lifts with two hands. And it's relevant if you have more than one lift in 5 minutes or more than 20 lifts in 8 hours. You have to reduce the weight limit by this load frequency in lifts per minute. Let me. There we go. So we have this set of lift limits for the population based on what task they're doing. And if they're lifting really frequently, we have to modify that using this equation here. So, using the military handbook, we can also make adjustments for the size. If you're lifting a giant empty box, it is harder than lifting a small empty box. And so all of these are adjustments for size. There's also adjustments for twisting, or if there's an obstacle or in some other way making it harder to approach that surface. So if you combine all of these different adjustments, you can determine what the appropriate lift limit is. Yes, Elizabeth?
Are WL and LM the same thing?
The weight limit and the load multiplier. Yeah, and in this case, they are. Yeah.
If you have like multiple of these things, like you would be twisting your body and as a
Yep, if you're twisting and you have you know, a depth greater than, yeah, so you multiply it by all of them. So you'd have your weight that you're a load limit, say that we have here. Let's say we take this one, and then you'd multiply it by 33%, by also 50%, or whatever else related to those other multipliers. Yep. And so we can modify these lifting abilities based on the frequency, the size of the load, twisting, and anything else. So that's one method. And you might notice in the slides I'm skipping ahead a little bit. Another method is the MAWL, also known as the maximum acceptable weight limit, or weight of load. And this maximum is determined by testing. The advantage of the military handbook limit is that it's really easy to apply. This amount of weight, do you have any twisting? Do you have any awkward sizes? What's the height of the starting and end position? Is there any weird obstacles? Done. That's it. It's a really easy thing to calculate. But what about other activities? There's a lot of other activities besides for lifting something up from a flat surface that's shaped like a box and putting it somewhere else. There's tons of assembly activities, all kinds of things. And so when you have a situation that you're assembling something, you're lifting something, or loading something that doesn't conform to that pretty standardized movement of I'm lifting something up, I'm moving it a small distance, and I'm putting it back down, then you want to use this empirical method for determining what a safe limit is. And so the way that you do this is that you test with participants. And this is useful for complicated tasks because the complicated tasks, there's two reasons that it's useful. The first reason that it's useful is that maybe the task is complicated and you have a special population, or you don't have a special population, maybe it's the general US population, or there's some other weird aspect of the task that in the military handbook would be, you think, unfairly penalized. So there's something that would be considered an obstruction, but you think, you know what, that's not really an obstruction. But if I use the military handbook, now we have this really high impact modification that lowers the amount of weight that I can have my workers safely lift. Well, if I use the maximum acceptable weight of load calculations by empirically testing that, I can determine what's a safe load for my user population empirically, and I could do that on more complicated tasks. So that's the first reason. The first reason is that maybe some of these other methods feel too conservative for you, and you need, because of the situation, you need to be able to lift something heavier. The second reason is in complicated scenarios. If you're doing something weird, like if you're loading those chairs into a truck, loading a chair into a truck is a very strange process. The wheels spin around, it's an awkward shape, maybe the arms start extending or shrinking in, or all kinds of stuff. And so using empirical testing is a much more accurate way of understanding a complicated loading or unloading situation. So you want to use representative samples. You want to use a number of tests over several sessions with several users. And then you want to be conservative and adjust downward. Anytime you determine a load limit when you're thinking about material handling, the goal is always to be conservative and adjust downward if you ever don't know what to do. Just like we dealt with hearing. Questions about this? Cool. So the next method is the Liberty Mutual method. And the Liberty Mutual tables, and this is the same company that does insurance. For a long time, they were one of the largest funders of physical ergonomics research to understand the risks associated with different tasks that they would then insure. So they had the Liberty Mutual Institute that did a lot of fundamental research in ergonomics that we still use today. And they actually sponsored the Liberty Mutual Prize, which is one of the most prestigious prizes in ergonomics. They don't have that institute anymore, but that's where some of these things came from. And the Liberty Mutual tables allow you to look up different types of movements and figure out certain weights based on these set of tables. In your slides, you have a number of examples of, or you have a workthrough of an example where you have this, somebody using the Liberty Mutual table to calculate a lifting limit. But I want to move on to one of the most popularly used methods, the NIOSH lifting guide. Is anybody here familiar with the NIOSH lifting guide? So the NIOSH lifting guide is the one that we're going to go through in more detail tonight, and the one that I want you guys to get practice using. That's why I haven't been going in as much depth the others. So the NIOSH lifting equation has a number of different factors that get multiplied by each other, just like Elizabeth was asking about for the military handbook. That if you have all of these different types of aspects, whether it's turning or awkward shapes, they all get multiplied together to figure out how they modify this load. The NIOSH lifting equation has a load constant of 51 pounds as the unmodified lifting limit. Was it actually Elena and not Elizabeth? I apologize. I'm sure that's never happened before. 51 pounds might sound familiar if you're a frequent flyer who checks luggage. The load limit for luggage is 50 pounds. It's not because the airlines don't want you to take heavier things, it's for the safety of the workers. So next time you have a piece of luggage and it's like 51.5 pounds, and you ask the person at the gate, like, can't you just let it slide and let me check this piece of luggage anyhow? Keep in mind that you're asking somebody to lift that, and that's why that limit is there. I'm not saying you should feel bad about it. It's your own moral compass around how you pack your luggage is irrelevant to this class. Anyhow, let's move on. So the NIOSH lifting equation has a number of multipliers. We're going to go through each of these in great detail, but it's important for you to understand conceptually what each of them are. So keep in mind that we're going to go through all of these. So we've got 6 different multipliers, and all of them get multiplied by this load constant of 51 pounds to determine what's an acceptable, a recommended weight that you could lift, depending on the task. So there's some assumptions here. The first assumption is that there's no unexpected falls or load changes. You're not sloshing around an aquarium, for example. You're lifting something with both of your hands in free space. You're not crawling through anything. There's no other tasks that are going on that require a lot of energy. You have a reasonable coefficient of friction between you and the floor. You're not walking on ice or in a greasy kitchen. You have no mechanical aids, and the lifts take between 2 and 4 seconds. They're smooth, and that there's not a really great distance between your hands. Just like the military handbook method, the width of a package makes it harder for you to lift something. And so the assumption here is that your hands are about this wide or less doing these lifts, 25 inches. So on our course site, there's a bunch of stuff on the NIOSH lifting equation. So this is our figure of our dude who lifts things. This is our homeboy that we're going to be hanging out with for the rest of the evening, and this dude lifts. And when he lifts, there's a few different things we want to take into account. We want to take into account that maybe his legs are not just straight next to each other. They're partly parted. We're going to talk about that position. And that he's standing straight up and down. He's got some vertical height between his hands and the ground. And he's holding on to something that's less than 25 inches wide, right? We've got this maximum spacing. What we're trying to come up with in using the NIOSH lifting equation is a recommended weight limit, this value here. And the recommended weight limit is based on the load constant of 51 pounds, as well as each of these multipliers. These are those 6 multipliers I mentioned just earlier, and each of them goes from 0 to 1. So the first one is the horizontal multiplier, HM. And it reflects how far away from the center of your body you're holding something. And HM, the equation for HM is 10 divided by H. And we're going to go into how to calculate H in just a moment. But it reflects that carrying something super far away from your body is harder than carrying something right next to your body. So if I'm designing a box and my box is super wide, it's going to be harder, or super deep, it's going to be harder for me to carry than if it's close to my body, because my hands are going to have to go further out. And so we're dealing with this distance out from the midpoint of the body. So remember I said that it's 10 HM, the horizontal multiplier, is 10 divided by H. Well, H is a few things. H, the equation, depends on the size of the thing that you're lifting, as well as the height that you're lifting. And so the size of the thing that you're lifting, if we think about holding this box, a box of width W, that if I'm holding it in the middle of that box, that's where I get W over 2 here in these equations. I'm holding it at the midpoint of the box. If I assume that the box is equally dense, then the center of gravity is there. It's not going to tilt. It's going to reduce the force in my wrists of rotation. That's another biomechanics static modeling thing, but we don't need to get into that. And we have two different options for H. The first option for H is 8 plus W over 2. And this is for any lift where at all points in time the operator is greater than 10 inches off of the floor. So as long as this vertical height is always 10 inches or greater off the floor, then you can use this equation. If at any point the operator goes below 10 inches, so they're picking something up off the ground or something very close to the ground, or they're placing something on the ground or very close to the ground, then you need to use the second equation. The reason for that, yes, Yifei? Yeah, they're constants. That's a good question. The reason for that is because as we bend over, at least some of us, have a belly that get in the way. And so we have to reach out further in front of us to be able to pick something up or put it down when we get really low. We have to account for our leaning forward. Yes, Elena?
So you would calculate the H's for both of your hands and then average them to find actual H?
Yes, Elizabeth, that's exactly right. I'm just teasing. But yes, you'd calculate the average H value. And then you're going to be plugging whatever H you calculate here into the horizontal multiplier. And what's important is to keep in mind that H is measured. Sometimes if you can't actually measure it, you use these equations. But if you can actually measure it, then what you want to do is you want to use the midpoint of the ankles to where the hands are. And that's why in this diagram we have the midpoint of the ankles between the 2 feet. That's why our buddy is standing with feet slightly agape. Yes, Elizabeth.
So just to clarify, the H equals 8 plus W over 2, that would be an H for one hand, and then you would find H for the other hand?
Only if the hands are in different positions. Yeah, so if you're holding something like this, then yes.
But if they're symmetrical.
But it wouldn't be W over 2.
If they're symmetrical, then you're welcome to do the exact same calculation twice and then divide it by 2, but you do not need to, because obviously they're symmetrical, so you just don't need to do it. It's not going to change the outcome.
So if they're asymmetrical, you wouldn't be doing W over 2, you'd be doing like W or...
Yeah, you might just measure the H for each of them based on where the ankles are and the thing. You could potentially. I mean, no, you wouldn't use W over 2. You might use something else. Next, we have the vertical multiplier. And the vertical multiplier uses this equation. And we use it for the origin and the destination. And remember our buddy, the V is the height of the hands off of the ground. So if on Black Friday you buy a big screen TV and you go to carry it home, well, I have bad news for you. You can't use the Nyasha lifting equation because your big screen TV is probably greater than 25 inches. If you buy a small screen TV, then you can use the Nyasha lifting equation. Or if you buy a really weird shaped TV that's 25 inches wide and really tall, you can still use the Nyasha lifting equation. And those handles in that big screen TV box, those handles aren't right at the bottom, right? They're part of the way up. Often they're pretty close to the top, so that the lifting height is closer to this 30 inches. that we have this as this assumption here. So we calculate the starting height and the ending height to figure out which has the smallest vertical multiplier. Because when we have a number closer to 0, it lowers the total recommended weight, which makes it more conservative. That's why it says take the lower value here. Next, we have the distance multiplier. The distance multiplier is not the distance that you're walking. It's the distance vertically that you're lifting something. So if I'm lifting, I don't know, a box, and I have to lift it up and then put it down, that's harder than if I lift it 1 inch and then put it right back down at that same height. And so the distance multiplier represents the vertical distance multiplier. It's an easy way to remember it. It actually is not any easier than anything else. But just remember the vertical multiplier was already taken, so they used the distance multiplier to confuse undergraduate students. But you guys aren't undergraduate students, so you're not going to be tricked. Yeah. Do keep in mind that the minimum D is 10 inches. On to the next term, the asymmetry multiplier. Any twisting of the torso is represented with the asymmetric multiplier, asymmetry multiplier. And so the modification for the asymmetric lifting uses A in degrees. Next, we have the frequency multiplier. And similar to the one-size-fits-all military 1472G handbook method, the frequency that you lift with has an impact on your strength. And so you have this range of frequencies where you consider modifying the recommended weight limit by the frequencies. And you have to look them up. And here's the table where you look them up. So you look them up based on the duration of the task, and the lifts per minute, as well as the height. Do we use the starting height or the destination height? The origin height or destination height for the V here? Whichever one is worse. So we see, say, for example, here, that if it's less than 75 centimeters, you have a multiplier of 0, whereas here, you have a multiplier of 0.13. At 0, that means it can't be done. You're multiplying it by 0, this load constant. So you always want to take whichever is worse if you go both above and below this 30-inch height. Next, we have the coupling multiplier. Yes?
And by worse, you mean closer to 0?
Closer to 0. That's exactly right. So worse is always the smaller multiplier. Next, we have the coupling multiplier. And the coupling multiplier deals with how easy is it to hold on to this thing? So the definition of good is when there's appropriate handles. Fair, there's no handles. And poor, if it's slippery or awkward. So what's the equation for the recommended weight limit again?
Times the multiplier.
51 pounds multiplied by all of these multipliers. That's exactly right. The recommended weight limit is the load constant, this 51, multiplied by the horizontal multiplier. That's how far away it is from your body. The vertical multiplier is the starting and ending height. The vertical distance multiplier, that doesn't help you memorize it at all. But the change in height, the asymmetry multiplier, frequency multiplier, and coupling multiplier. And we use the recommended weight to tell us how much should we allow for a weight for this task, or to calculate a load index. Sorry, a lifting index. And the lifting index is the actual weight divided by the recommended weight limit. So if we calculate that it's safe to lift 10 pounds, but we're asking somebody to lift 11 pounds, we're going to get a lifting index above 1. Lifting indices above 2 is where you're going to start to get complaints from workers, and you're going to start having workers experiencing stress. Above a lifting index of 3, you're going to end up likely having workers experience injury. And if you're trying to prioritize where to spend your money in improving your factory, you can sort by lifting index to figure out where you should spend your money. So questions about the NIOSH lifting equation? Yes?
Where did the 51 come from again?
The 51 is the load constant, and it was empirically derived. The NIOSH lifting equation has been tested through empirical studies. So just like the maximum acceptable weight of load, the NIOSH lifting equation is basically that for some very standardized tasks, where it was done over and over and over with a large range of participants. Other questions? Yes?
Is it possible that one of these things would end up being 0?
It is. In which case,
What happens?
what?
Then what happens?
Don't have the person do that. Yeah. Or adjust it so that it's not 0. So have 2 people do it if the lifting frequency is too high. Add handles if because the modifier is too low. Now the coupling, you can't have 0. Asymmetry, you certainly could, right? Yeah.
What if you're pushing something along the floor so it doesn't have any distance there?
Good question. So the question was, what do you do for pushing? And the answer is a different method. That'd be the maximum acceptable weight of load. The NIOSH lifting equation is only for lifting. It's actually a really interesting question. I've been talking with another researcher about doing some research because there's not a lot of good research on acceptable weights to push. And so we've been talking about actually doing some of that for a master's student research project, if you're interested in studying pushing things as a master's project. So, other questions about the NIOSH lifting equation? Yes, Yifei.
About
Yeah, so if you're lifting something and moving it sideways, that's not accounted for. That'd be accounted for in twisting. Yeah. I understand that it'd be possible to do this, but you'd account for it in some sort of twisting motion. The vertical, the distance multiplier is just the vertical height that's covered. Okay, it's 7:51. Let's take a break and let's come back at 8:05 and we'll go through an example. Rodney, can you hear me? Excellent. All right, so we've just finished calculating the lifting index, the NIOSH equation, so let's go through a chance to practice it. Sound good? I know. Okay, so at Squawk Box TV Company, associates lift a TV chassis from a conveyor to a handling stand, which is then rolled away by somebody else. The conveyor rate is one chassis every 10 seconds. So a conveyor comes down, they've formed the chassis, they lift it, they put it onto a handling stand, and then that stand gets rolled away. The conveyor is 3 feet off the floor, the stand is 2 feet off the floor, and 90 degrees from the conveyor belt. So they turn 90 degrees. The chassis is 18 inches wide and 26 inches deep and does not have any handholds. So there's no handles on it. The associates stand 3 inches back from the conveyor and 3 inches from the stand. So they're standing there kind of partially turned. They pick up the chassis, they put it down. Pick up the chassis, they put it down. And they're 3 inches away from whatever they're picking it up from or putting it down. So let's calculate the NIOSH lifting recommended weight limit for this. You guys want to go through it on your own? Okay. Well, it's not. Fine. What's the maximum weight that we can set up the chassis to be with this arrangement? Well, we know that the load constant is 51 pounds. So the maximum, if everything was perfect, we couldn't have it weigh more than 51 pounds to begin with. But the horizontal multiplier, remember it's 10 divided by h. And here, h is going to be the 8 value because we're above this minimum height of 10 inches. Remember, if we're picking things up off the floor. Then we have half of the depth of the TV, so you're holding it halfway from the front to the back, plus the 3 inches that you're standing back from the conveyor belt. So you have to reach a little bit further because you have this, you don't want to get hit by the conveyor belt right as it's going by. And so we have a horizontal multiplier of 0.42. Next, we have the vertical multiplier based on the height. And we have the vertical multiplier of the starting height. That's what the O here is, of the origin. And we calculate the starting height is 3 feet. So we have this starting height, we calculate 0.96 as the multiplier. But we also have to calculate the destination height. Well, the destination height is 24 inches, 2 feet. And so we have the same multiplier because both of them are 6 inches off of 30 inches, and we're taking the absolute value. Next, we have that vertical distance multiplier. I know, you're probably thinking horizontal distance, but not, because Dr. Nathan Roberts reminded me that it's vertical distance, and he's gone over that point a bunch of times, and it's confusing that they call it distance multiplier even though it's vertical distance multiplier. Whew. Sure, that's went through your head, right? And so we have 0.82 plus 1.8 divided by 12 inches of change in height, because it changes from 3 feet to 2 feet. They lift it up and they put it down.
Where's 0.82 coming from?
That's part of the multiplier.
That's part of it.
The multiplier is the distance multiplier is 0.82 plus 1.8 divided by the change in height.
Where did the 1.8 come from?
The 1.8 is also always a constant. And basically, they're there so that you always, if you have a multiplier of 10, which is the minimum value that you can have for this number of change in height, remember it's 10 or anything larger than 10. If it's smaller than 10, we still put 10 in there. 10 or bigger. I should write big, super big. Bigger. Right? It's 10 or bigger, and as a result, if we divide 1.8 by 10, then we end up with 0.18, which we add to 0.82, and we end up with a multiplier of 1, so it doesn't decrease the total height or the total recommended weight. That's why that value is the way that it is. Next, we have the asymmetry multiplier, and we include the number of degrees here. So they're turning 45 degrees in each direction or 90 degrees. I mean, I guess suppose they could be turning some other really weird position, but we're assuming that they're going to position themselves either facing one of the two conveyors or kind of halfway in between. But the total rotation is 90 degrees here. And next, we have to check the frequency multiplier. So with one chassis every 10 seconds, that's 6 chassis a minute, 6 lifts per minute. It's an 8-hour shift, we're assuming that our associates work. And we have a V of either 24 or 36, the starting or the destination height. And so for an 8-hour shift, when we look up the work duration, 8-hour shift, so we know we're going to be in one of these two columns here. For less than 75 centimeters, which is 30 inches, which would be the destination height, 24, or for higher, the multiplier is 0.27 for both of them. So we don't need to change it for just one or the other. The multiplier is exactly the same. And lastly, we have the coupling multiplier. If we go back to the coupling, we have a coupling of fair here because there's no handles. And with no handles, we have a height less than 30 inches, so we're going to have a coupling multiplier of 0.95. Oh, I'm sorry, the TVs are large. Yeah, apologize for that. So we have a coupling multiplier of 0.9. So as a result, when we multiply all of these together, we end up with a recommended weight limit of 3.4 pounds. That seems really low, doesn't it? The chassis for the TV would be only 3.4 pounds. That's like one large box of pasta, not even a Costco box, just a large box of pasta. But if we think about the associate doing this just for 6 hours, not even the full 8 hours. So if they get an hour-long lunch and they get 4 15-minute smoke breaks, then they've lifted 3.7 tons that day. That's a lot. So it might not seem like very much, but that's a lot. So if the actual chassis for the new model weigh 8.5 pounds, then we have a lifting index of 2.5. And with a lifting index of 2.5, you'll expect some workers to want to change jobs. You'll expect some discomfort, some complaints, but it is feasible to be done. Questions? Yeah, Elnaz.
Horizontal multiplier.
Sure. So let's go all the way back to where the horizontal multiplier comes from. The horizontal multiplier, here we're going to assume that the left hand and the right hand is the same. The horizontal multiplier, as long as it's greater than 10 inches off the ground, is going to be a value of 8 plus the depth of the box divided by 2, as well as any other space. And so we have the depth of the TV here. If these are the TV chassis, the depth of the TV chassis is 26 inches, plus the worker stands 3 inches back. And so if we take this 26 divided by 2, we end up with 13. We add 8 as the constant because it's above 10 inches at all points in time. And we add another 3 inches for this space so they don't get caught in the conveyor belt.
And then the 26 came from just the depth, right?
Yes, the 26 came from the depth of the chassis.
And that 3, that's the distance from the worker to the box. We don't add that?
You do add that, yes. So let me go back to the example. The associate stands 3 inches back from the conveyor and 3 inches back from the stand. So in doing this calculation, for the horizontal multiplier, we have 10 divided by 8 is the constant. 13 is 26 divided by 2. That's the depth of the entire chassis divided by 2. So they're holding it halfway through. And then 3 inches for the conveyor. Sure. Yeah, Rohan.
And for the frequency multiplier, it was referenced that V is either 24 or 36.
Mhm.
So we have the two numbers. So is there ever a case where it's not the same? Like in here, it just happened to be both 0.27.
Yeah, so it starts to not be the same when you get into the areas where it gets down close to the bottom.
Okay.
So let me find a good example for you. Well, so where it becomes 0 is certainly one of the places where it's not the same. But there's a few other places.
That it was different. How would we then? Would we have two separate RWLs?
Good question.
And as just apply it as a range? Or
Yeah, if we have two different multipliers, what do? You always take the lower number to be more conservative
So
on your
that's what
lifting
you were
index.
referring to a while ago.
Absolutely. But this is true for the height, the vertical multiplier. It's also true for the lifting index. It's also true for the coupling. If there's one side that's got a really nice handle, the other side is made out of ice, well, you're going to use a really poor coupling multiplier. Yeah, Ian.
So with the L1, and say they ended up doubling the weight?
The lifting index, LI.
The lifting index?
Yep.
So set it to lifting index 2 or 3, wherever the injuries start to.
Yeah, that's 3 is the lifting index.
How would that translate to the 2.5 then? Would that be twice the amount?
So if this is the recommended weight, and if the lifting index I equaled 3, then we'd have the actual weight would be about 10.3 pounds or so.
Oh, okay. So the two,
And the recommended weight would be 3.4.
okay.
Yep. Yeah, Ashta.
Yeah. So why are we dividing 26 by 2 if we are holding the chassis from the bottom?
You're dividing 26 by 2 because the depth of the chassis in this direction is 26 inches, not the height. Yeah. Good question. Sure. Anything else? Well, all right then. So, briefly, I'd like to go over a couple of countermeasures with you. There's a number of different countermeasures, and they relate exactly to the equations that we were dealing with, right? So, if the asymmetry multiplier is causing you to have a very low recommended weight limit, then changing the rotation, minimizing the rotation, is going to improve the safety as well as the weight that people can use. The weight itself obviously has an impact. The coupling has an impact. Reducing the horizontal multiplier has an impact. All of these different values directly correlate to the Nash lifting equation. One of the ways that we can do this to adjust these things are using any of these types of tools. So a lift table that includes something like this, where you can actually either pneumatically, electrically, or even sometimes with springs, lift things automatically for yourself or reduce the amount of weight to lift things. You can use a forklift, cranes and hoists. All of these other different things can reduce either the need for lifting completely or the load frequency or the load or any of these other things, so that we can have workers safely do these tasks. Questions